In the example from the previous video, eigenvalues and powers, the eigenvectors v1 and v2 were a basis for R2. And this was what allowed us to use that method to compute a to the k times x for any x, and in particular for the vector 5, 1. However, unfortunately, we can't always find a basis for Rn consisting of eigenvectors. For instance, from finding eigenstuff, the matrix 0, 1, 0, 0, 0, 1, 2, minus 5, 4 has two one-dimensional eigenspaces. So, in particular, the eigenvectors don't span R3. Okay, we figured out that we can't expect them to span. What about linearly independent? We can't completely say that all eigenvectors are linearly independent from one another, because, I mean, if I have one eigenvector and then I multiply it by 15, I get another eigenvector, and those two eigenvectors are certainly not linearly independent. However, we do have the following theorem. If v1 through vm are eigenvectors of A corresponding to distinct eigenvalues, lambda 1 through lambda m, then v1 through vm are linearly independent. That distinct is crucial. Otherwise, this is, as I said before, not true. I'm not going to prove this in general, but I'm going to prove the case m equals 2. So proof in case m equals 2. The general proof is not substantially different. So suppose that v1 and v2 are linearly dependent. We're going to get a contradiction. Well, then v1 must be equal to c times v2 for some scalar c. That's what it means to be linearly dependent. But then a times v1 is equal to a times c v2, which is equal to c times a v2. But this guy here, that's equal to lambda 1 times v1. That's because v1 is an eigenvector of A corresponding to the eigenvalue lambda 1. And over here, we have c times lambda 2 v2 because v2 is an eigenvector of A corresponding to lambda 2. But we know from our assumption right here that c times v2, so this is lambda 2 times c v2, that this thing is equal to lambda 2 times v1. So in other words, lambda 1 v1 is equal to lambda 2 v1. But v1 is not 0. So that means that lambda 1 must equal lambda 2. But this is false by assumption. So therefore, our original conclusion that v1 and v2 are linearly dependent is false, and we therefore conclude v1 and v2 are linearly independent. Tombstone.